So we're starting with our last session, 2 talks left for today before we go to the barcamp. And I have the pleasure to introduce Gennady and Atakan from Idealo, and they will share their journey into hybrid search at Idealo. Please welcome our speakers.
So, yeah, it works. So, hi everyone, I'm Atakan, a machine learning engineer at Idealo. Also, Gennady is a machine learning engineer. So today we would like to discuss what we did hybrid search at Idealo and what was our journey, what was our learnings. So before starting, so there are lots of talks about hybrid search in MICES, really great talks from Roman and from the others, lots of companies. Also today, one of them from DM. So these also helped us, inspired us while building everything. And yeah, today we would like to skip the maybe motivation parts a bit. At least we will talk a bit less because I think it's an e-commerce search conference and everybody is already motivated for hybrid search, I hope. So yeah, starting with the agenda, first I will introduce Idealo as a company, then we will motivate a topic, then I will talk about vector search fine-tuning, the decisions that we made, the experiments that we made. Then Gennady will talk about the hybrid search strategies and the model serving, the challenges we faced, and then we will close with the key takeaways from our lessons. Yeah, so about Idealo. Idealo is a price comparison platform, if anyone of you doesn't know. So it's the 4th largest e-commerce website, and we have a huge catalog with 8 million products and 500 million offers. And we are really active in Europe, so six different countries: Germany, Austria, Spain, Italy, France, and the UK. So would like to introduce the catalog a bit because it's a bit related. It increases the complexity for us a bit while building hybrid search at Idealo. So maybe the ugliest page today. Sorry, it's so many human interruptions to the cloud. So sorry for that. So on the top left side, we see a search result product item, which is iPhone 17. So we have those products, more than 8 million of them at Idealo. And when you click on these items, you actually go to a product details page, and you also see the offers on the bottom side, cheapest to the most expensive one. But which makes everything more complex is the unassigned offers, single offers. So you also have those items here, and there are 500 million of them, as I said. And when you click on them, there is no product details page. So you just directly go to the merchant's website. So these are not assigned to any product in our catalog. So we have to also get the vectors for all of these. So which makes more than 500 million embeddings in total. So for the last 25 years at Idealo, we have a keyword search backed by Lucene, maybe surprising for some of you because there is no open search, there is no Elasticsearch or Solar, so it's backed by Lucene, a customized Lucene structure. And we have lots of manually tuned boosts over the years, so lots of domain knowledge there. And especially the most important ones are historical global item clicks and query item clicks, which affect the rankings just before the learning to rank algorithm. Yeah, so we also mentioned today in another talk in DM, so there are lots of strengths and weaknesses of this keyword search, as all of us know. So it's really good at exact matches, it's really fast, and it's easy to debug compared to vector search. And for the weaknesses part, vocabulary mismatch is critical, so it's a bit tricky to handle with keyword search and semantic queries, lots of different weaknesses there. So that's why after looking at the problems of keyword search, like the spelling mistakes, semantics, and different languages. And actually we can have some solutions to fix them, but the thing is these are not scalable. We also talk in merchandising, so we can provide some synonyms, we can provide some rules to fix some of the issues or fuzzy search, but the thing is it doesn't scale to all of the long tail queries. The thing is in e-commerce search, every day you should expect at least 20 to 40% new queries, so you don't have any user interaction data on those, and you actually need vector search there and the power of the keyword search together. So we said that why not to use both, then we start this hybrid search project. So before diving into the topic in detail, just a high-level overview here, what will be the end. So we have a searcher endpoint, and Here we have Apache Lucene-backed backend service, and we have the vector search endpoint, which is backed by SageMaker endpoint. Also the LTR reranking endpoint. Actually, the details of LTR is from last year MICES. We also gave a talk, so if anyone is interested, the details will be there. And what it does is, so user enters a query at Idealo. So we go in parallel to Apache Lucene and the vector search. We bring some items as the candidates. Then we provide all the items we get from these two sources to the LTR endpoint, and it just re-ranks the items. Then the user sees the results. That's the main flow of the whole architecture. So before starting a vector search project, there are lots of decisions to be made, actually. So for instance, the relevance labels of query item pairs, what you should do there. Should you just label it manually or use implicit feedback from users? And pre-trained models is it easy, like you go to the Hugging Face and you just check MTAP leaderboard, you look at the retrieval metrics and what is the best one, just look at cost and latency there and pick the best one. And also the loss functions when you fine-tune these sentence-BERT models. So there are lots of decisions to be made just before starting. So that's why actually in the first run, we just choose 6 different models. These are also by looking at the metrics in MTAP leaderboard and also hearing from the others, the blog posts. And we create the test data from Idealo's user interaction data. Then we create a test set. Then actually we would like to get our own metrics in our data because it really changes between the data sets and the domains. And when we look at the results, so surprisingly, E5 family was better than the others. So the embedding models were Gina embeddings v3 on that time. It was the latest. So QN3 embedding, which is the biggest, I think, in these 6. And Alibaba model from GTE multilingual base, also the E5 small base and large models. So when we look at the results in our data set, E5 family was the best one. And also the bigger it was in E5, the better the NDCG there. But the others didn't perform well enough for our use case without fine-tuning. By the way, we don't have the results here, but especially after fine-tuning, we also see a similar ranking, at least from each other there. So here we also consider the cost and the latency, and we said that, okay, we can continue with multilingual E5 small. So we chose that model as DM did today, so it's not that surprising again. So how fine-tuning works after choosing multilingual E5 small. So we also chose the multiple negative ranking loss here. So what it does is we have a query from historical data set, let's say. So we have user interaction data, and according to that, we choose some positives and negatives, products and offers in our case. Also we use title, category, manufacturer, product types, and all attributes of our products. Then the loss function and the model is just trying to increase the cosine increase the cosine similarity between the query and the positive item, and try to throw away the negative items from the query. So that's what it does actually. Also, it uses in-batch negatives, some random negatives from the same batch to get some better performance in the training stages. Then I will pass on to Gennady.
Yeah, hi. We have chosen this strategy of training, so this multiple negatives ranking loss. So the question is how now we choose our positive and negative. So that's the main question actually for that problem. And we just simply try different options, different combinations, how we can choose positive and negative. One comment, right? So positive item should be something relevant for the search, and usually it's the item with the highest CTR. Of course, we have some problems with position bias, but usually it's like this. The high CTR item is the most relevant. And the item without clicks at the very bottom at our search result, it's usually the item is the least relevant. And since we want to find like some hard negatives, so we want to choose a negative from the same search result because it matches your query, but it's hopefully it's irrelevant because it has 0 clicks, such that that model can learn something. And it doesn't make sense to provide some random negative, so the model doesn't learn anything from that, and then experiments show that as well later. So, and then different combinations, right? First and last. First, it's the approach we tried is that positive item, the item with the highest CTR, negative, the one with 0 CTR at the very bottom. Then you take like all positive, like those which has some non-zero CTR, the same with the very bottom item. And then we also tried just simply take only positive. And because we have problems with selecting negative, so we thought, okay, maybe let's choose only positive. And then different combinations, right? So you combine, let's say, every positive with all negatives. And one also selective negative approach is that when you select like top positive and then negative comes, the negative should have different category than the positive item, such that you know for sure that it's kind of negative from the central result, but it's kind of really like maybe it increases chances that it's not like wrong negative, false negative, I would say. And this is our experimentation results. So we just put some top results here, not everything. So the winner is that you have this approach when you choose only one first positive and the very last item is a negative. And if you increase batch size, it also makes your results better. It's also about attributes. If you add items attributes, it also improves our results, and we kind of why we make it special, like consider with attributes and without attributes, because attributes are quite noisy. So if you have like some iPhone item, it has like hundreds of attributes, many of them irrelevant, and we thought, okay, maybe it doesn't make sense to include them. But actually, even if you include noisy text, it's still like relevant. And this, if you include only positive, it's basically has the worst results. It's not even here on that plot. So it indicates that you need hard negatives. Even sometimes you can make mistakes about hard negatives. So the Atakan will talk about this as well.
Yeah, so I think this is the most important part for the fine-tuning part for the vector search. And yeah, hard negatives are very important for the model to learn stuff. But the thing is, after choosing positives and negatives, we just checked some queries, positives and negatives, randomly to understand how it looks with the strategies. And as you see in here, so for this Ketazoline shampoo query, we have 6 different results returned, so not more. So when we look at the results, actually, we saw that actually not all of the queries should have any negative. I mean, some of the queries, of course, will have negatives, but for instance, in this example, the user didn't specify any size or anything, but all of them are more or less the same. So actually, these kind of examples confuse the model to learn the negatives, because as I said in the fine-tuning part, we try to put the query and the negative item far away, but in this case, it didn't work for us. So that's why we said that, I mean, it's actually a CTR equals 0 item. It was a long tail query, so not that much impressions. So probably that's why this was a negative. And then we said that, okay, how can we solve this issue? How can we identify the at least false negatives? Then we said that, okay, maybe we can, it's 2026 and we can use LLMs for this, so they might help on this topic. So we conducted multiple experiments on this. Actually, we conducted tens of experiments, but I just tried to put 3 of them here. So we have a baseline here. Baseline is from the previous slide, the best model on that time. So a positive item and a negative item and a query. So in the experiment one, what we did was we provide all of the queries and the negatives one by one to an LLM. On that time, it was 4.0 mini. So pretty old, I think, in terms of LLMs right now. And actually, what we saw was 25% of the queries negatives were eliminated. So we used random negatives instead, these false negatives. Also in experiment 2, we said that, okay, maybe we can directly generate some hard negatives and negatives for the queries. Just a fun experiment. We wouldn't expect a really high performance for this. And for the last experiment, we provided more negatives with the LLM by using also the CTR negative, let's say. And then again, in our test data, we calculated NDCGs and we saw that, okay, in experiment 1, using this LLM kind of negative filtering worked for us in our test data. But as we see in experiment 2, learning is, I mean, ignoring our negatives and generating with the LLMs are, I mean, not worked at all on that time. Also, experiment 3 was good, but we got the best results with the experiment 1 by using LLM filtering. So Gena will continue with hybrid search.
Okay, so you figured out how you want to train your vector search model. So now the question, how you want to integrate it into your search. So basically you have already keyword-based search, you have now vector search, how to merge them together. And we have already learning to rank in production, so we want actually teach somehow our learning to rank our vector search items together with keyword-based search items. But the problem is that learning to rank have never seen these vector search items, they don't know how to rank them. So that's why we kind of integrated vector search in 2 phases. So first we just append vector search items at the end of keyword search results for few result searches, and then just run A/B tests. Okay, it shows good metrics, so all good, like release in production, and then we start collecting the metrics, and then we start collecting how user interact with these vector search items along with the keyword-based search items. So, and then it's actually training data for us. So, and then we basically what we do, we just collect the statistics and then we just train our LTR, but new trained LTR already knows about, for example, the vector search similarity score of the items. So, and it knows when the user click on vector search items, when it doesn't click. So it's trained, right? So, and then we do kind of full rollout. So we basically just, okay, we have two searches now, we merge them, so we just we do it for every search. And then LTR decides when to show more vector search items, when to show more keyword-based search items. And we also did again A/B tests. All good. So we tried also, like, of course, alternative approach, which is easier. It's RF fusion. And it's actually easier to integrate because if you have already LTR in place, then after LTR you can just fuse vector search items using RF fusion, which is also kind of, it's simpler. And okay, so, and this is our A/B test results compared to control group. So it looks good, so it's for every search at Idealo. And it's actually not cumulative, cumulative gain. So as so I was thinking why we didn't do this, because we also have had positive results when we introduced it for 0 result searches. So it's already a control group contains already vector search result for few result searches. So that's why I think the numbers are big, should be a bit bigger, maybe 2%, something like that. But it's also like for our scale, it's really good numbers. Yeah, I think that's nothing to talk more about this. So, and then now challenge scale. We have 600 million items for Germany, so hybrid search works for Germany. And now how we wanna index it, where we should put it. Like backend team just tried to put this 6 million, just these 6 million products into their Lucene index, so they were not happy already. And then to put 500 more million offers was not also for them good idea. So we decided to build a separate index. The first idea came into my mind just to see how vector search works, just to play around with that, just to put it into S3 vector index. So it was appeared just recently at that time, I think. So it was super easy to put. So you just put it there. It's cheap, right? So we just during one day you can put all our items in the vector index. So it costs like 500 euros only. But the problem is it's not it doesn't fit for production because its latency is 600-700 milliseconds per lookup. So that's why we tried a bit to play around with this, and then we come up with this solution. So for products we use like HNS-W index. Maybe you know HNS-W index is just the index basically behind most of the vector search databases. And then we just use raw HNS-W index. And it's for products for high precision. And we also use this phase inverted index plus a product quantization. So actually in phase, the more words you have in their index name, the less precise it becomes. So that's why it's kind of offers, we don't need that much precision for offers, so it's kind of, yeah, so it can be less precise. So one peculiarity about this index is that you need to train it. So basically you have your items, you take, like you should find some representative of your data. So like centroids, you run k-means clustering on your data. And then you have some centroids. And when you search, you just basically first, and every centroid represents your like some cluster of data. And then you search only first across your centroids. And then when you found centroids, close the centroids, then you search inside the clusters of the centroids. So that's why it reduces the space. And then product quantization is basically quantize the embeddings. So it makes them more compact. And then it makes the average latency 60 milliseconds, which is good enough for us. Okay, then, yeah, and then training, so it's easy, right, to create embeddings. You can parallel, you can make it parallel, it's quite fast. So one bottleneck is training. It's like, because you should choose CPU index, and then you cannot make parallel training. So you just, it's one instance. So you should wait when like this index is trained. So when you do clustering, and then for clustering, we basically also cannot choose all the 600 million items. We choose only like some percentage. We choose 15% of data randomly, and then we like select train, and then find some clusters. Like I think, I don't know how much. It's 6 million clusters. I think, I don't remember. And then and then in parallel we add vectors. So, and then here you choose already. So it's like you were add vectors in parallel, so you kind of have shards, right? So at the end, right, because you you pass this index to instances, and then you just in parallel add items, add embeddings in that trained index, and then you have kind of, depending on the amount of instances, you have like this n amount of shards, and we choose 10. It's like more kind of reasonable number. Yeah, at the end you have 72 GB instance, like 72 GB index size in RAM memory. So we keep everything in RAM. So so you can take instance where you can fit this amount of data in AWS. Yeah, and I think that's it. Yeah. So our takeaways, right? Of course, fine-tune your data, that's for sure. Hard negatives important, right? It's very important. Zero CTR, it doesn't mean it's irrelevant, so, but I think in search community, everyone knows it just because of this position bias problem, right? Or many bias problems. And better batches, right? So it depends on what allows your GPU. Like the bigger batch, the better. For that loss, multiple negative loss, how it's called. And then, what's that optimizer tool for? It's Atakan created. What's that?
So recall is important. So the thing is, we can get many items from vector search, so the recall is important there. The main aim is to increase the recall because the LTR does the job to re-rank them. So we just increase our recall, then LTR works for the precision here.
Yeah, basically you can just put small threshold for similarity for vector search, and then LTR can handle everything, right? And then, yeah, we need kind of think about scale. I guess that's the takeaway, number 6. Yeah, that's it. Thank you very much.
Thank you very much. Do you have questions to Atakan and Gennady? Oh, okay. This way. There was one here.
Hello. Thanks for the presentation. I'm not sure I understood correctly. When you talked about LTR, it was like So you either run a keyword-based search or a vector search based on the learnings that you acquired with LTR, and you don't run like a hybrid search together, no? Or how does it work? I mean, how do you make the distinction? Is it a hybrid search and then you get the results from both, or you run either of those based on some criteria?
Yeah, got it. So we have a keyword search. We get, let's say, n items from keyword search, top n items. Then we also run this vector search. So these are two separate things. So also we get top n items from vector search. Then we have n plus n items. Let's say n plus m. There can be duplicates. So vector search and keyword search can return some duplicate items. But at the end, you have some items coming from two different sources. Then what we do is we provide all of the items together to the learning to rank model, which is a machine learning based model, a tree-based model. So they just re-rank them, so the users will see those results. So this makes the hybrid stuff. So we have combining keyword and vector search items together with LTR. So these are all together. I hope it answers your question.
Hi, thank you very much for presentation. I have a question about explainability of hybrid search. So how you tackle this issue for your stakeholders if you have this issue?
Oh, we have issue only like average KPIs. And you mean like when you, let's say, run and it shows something and then you don't know why?
So you have country managers or some other people, category managers, and you need to explain why it's ranked like it's ranked.
Yeah, we don't, luckily don't have this problem. Basically for us it's just important in average how it works. Of course there are some specific cases when it's just bad, right? So, but we always check like in average what it gives in average. Yeah. So regarding explainability, so no, we don't. For LTR, for example, we can just plot some shape values and then show, okay, that's. But for vector search, yeah, luckily no. But I don't know. Atakan, do you know something?
Maybe I can add something. So it's really hard to explain actually. But for a couple of cases, for instance, our product came to us and said that, okay, why are these items are coming for this query? It's not really relevant. So what we did on that time was, we didn't work on this explainability topic at all. But what we did was we checked the training data for vector search fine-tuning, and we just checked some similar queries there. And for instance, for this ketazole in shampoo example, we found it by actually looking at the results. So we saw a query like this, we didn't like the item, and we just tried to look at the training data, and actually we saw that this was a negative, so that's why it's just pushing a relevant item to the bottom. Mm-hmm. So manually, I would say, just checking the data and this, so no systematic something to trace them back. I think it's really hard to understand sometimes.
Thank you.
Actually, yeah, ketazole shampoo, it's a good example, yeah, because if you now go to Idealo and you enter ketazole shampoo, you will see some irrelevant yellow things which are in top, I don't know, 20. If it comes from vector search, actually, because of like not very well resolved problem of hard negatives. We filtered this for ketazolene, this like hard negative, these negatives, but it's still, we choose random negatives, but it's not enough for kind of vector search to show all relevant items. So that's why it injects some kind of something which is not very relevant for us. Yeah. Yes.
Can I have a second question? Okay, quick one. Yeah, before when Zalando presented, they talked about they don't have zero results really, so they always show something. Do you always show something even for some strange queries? Or you have some cut threshold?
Yeah, we have threshold, yeah.
Okay.
Yeah.
How you found it?
Huh?
How you found it?
It was like we have some UI tool. You just first you play around with this and you understand this roughly the threshold. But you should sometimes like if you like we have a 0.6 exact number. If you put 0.7, it's just too small impact. So it's just vector search then returns quite rarely something. And then 0.5, it's already too much. It's too much noise. And then 0.6, it's quite of just sweet spot.
Okay, I know there's at least one more question, but we're a bit out of time. Thank you both again, and I guess you'll be around for questions, and we can also make it a discussion group in the Barcamp, talk about hybrid search if you want.
Maybe,
so let's thank our speakers again.
Maybe one last thing.